So, in today's video, I'd like to tell you a bit of a story about something that happened while I was trying to put together uh, an explorer for mathematical formulas. So, in order to understand what's going on, we need to start with something unusual that happens in a lot of modern programming languages. And I want to show you this in Python, actually, because there's an absolutely hilarious example of this happening in Python. So let's say that, for instance, we wanted to make a 4x4 matrix of zeros. So one of the interesting things that you can do in Python is you can take an array and multiply it by 4, and that will produce the array added to itself 4 times. And so if we wanted to produce a 4x4 matrix of zeros, we could just take that and then multiply that by 4. And here we go. We now have a 4x4 matrix of zeros. And now suppose that we wanted to, let's assign that to something. Suppose that now we wanted to, and again, here's the matrix, nothing's happened yet. Suppose that now we wanted to change one of the elements in that matrix, and let's change it to a 1. And now let's take a look at the matrix again. And what you'll notice is that not only did we change the entry at 1, 2, but we also changed a bunch of other entries in the matrix as well. So why did that happen? What's going on here? Well, let me show you something similar happening in JavaScript. JavaScript, I don't think you can get it to do this multiplication notation, but we can do something. Oops. But we can do something similar in JavaScript. So I'm going to have a var a equals 1. Var b equals a. And this is going to create a structure that's exactly the same, or at least close enough to the structure that we had established in Python. So in particular, here we have our object C. It's going to be an array of, I have made it a matrix of 1s, but that's okay. So here we have our object C. It's a 4x4 matrix of all 1s. And now let's change one of the elements. Let's change this to 2. And now let's take a look at our matrix again. As we can see, the same sort of thing happened where all of the entries with that particular index got all of the entries in particular column wound up getting changed. So what's going on? Well, it turns out that we actually have two different types of assignments going on here. So when I say a is equal to 1, the computer just knows that a is variable and it stores a 1 in it. Here, when I say var b is equal to a, it says, oh, well, this is 1, 1, 1, 1. Okay, I'm going to take that and I'm going to store that in b. And what's actually happening, so this is something back in the days when people used to code in C. People still code in C. C is still a highly relevant language, and I encourage you to learn it because it really gives you a sense of what's going on underneath. A lot of programming languages nowadays kind of try to sweep under the rug a lot of details in terms of what's actually going on in terms of memory management. And I think it's really important to know what's going on in terms of memory when you're working with a computer program. Not for optimization reasons necessarily, but just to understand what's going on with your code. What's happening here is that B is actually being assigned to kind of a pointer. So back in the days of C, we actually had real pointers, but in JavaScript and in Python, well, the kind of pointer variable line is a little bit more blurry, a little bit less clear to a user. What we're doing is we're saying that B is going to point to the place in memory where we're storing this array, right? If we have an array, we don't know how much memory it's going to take up. It could take up a whole bunch of memory. It could take up very little memory. And so what we did back when we had to actually worry about doing this stuff ourselves was somewhere in the memory we would store this array, and then we'd keep track of where in the memory the array was. And so in some sense, B is a different sort of variable than A, in the sense that B is keeping track of where in the memory this data is, and A is actually keeping track of the data. And so when we say C is equal to BB, that's just a bunch of pointers to this array in memory. And so then when we make this change to C, it's actually going to change each individual instance of B. Right? This change here is going to change. It's going to change element in position number 2, which is actually the third position because we start counting at 0. It's going to change the element in the third position of the second element of C. The second element of C is B, and so it goes into memory. It finds, it says, oh, this is a pointer. So I'm going to change the third element of B. And what that does is, because all of these other elements in C point to the same place in memory, they point to the same place that B is pointing to, that it actually makes a change to all of the elements in that array. So just to kind of give you kind of a basic sense of what's going on in terms of, this is something called assign by reference. Or again, we can talk about this in terms of pointers and go back to like the historical origins of this sort of assignment. But what's happening here is that when we say C is equal to BB, we are assigning by reference. And when we're saying B is equal to AA, we're assigning by reference. We're saying that B is actually just going to point to where this piece of information is stored, as opposed to actually being that array in some sense. So a little bit confusing. And again, if you don't have a background in C, you're like, why is the programming language treating A and B differently, right? It seems kind of strange that we have two different variables and they're being treated very differently, because we're also kind of making a change to A, right? We're taking a thing that is an instance of A and we're changing it so that it's 2. Why aren't we changing all of the instances of A? Well, it's because A is a different type of variable than B is. Specifically, A is referring to an integer and B is referring to an array. So B is actually secretly a pointer. So anyway, I mean, there's other places you can find out about this, but I just wanted to introduce this so that I could talk a little bit about a piece of code that I put together a while back. So let me show you what my goal was. My goal was to put together a piece of software something like this, where the user could type in a formula. It would get passed to Khan Academy's. So Khan Academy has some absolutely wonderful JavaScript libraries. They aren't perfect, but they can do a whole bunch of things with symbolic algebra and just working with formulas, displaying formulas, things like that. So one of them is called KAS, KAS.js, and that specifically deals with the formula side of things. And then Khan Academy also has KATeX.js, which takes a string of text and turns it into a string of HTML that you can then just insert into your web page and display a formula as if it had been rendered by something a bit fancier like MathJax. So anyway, I wanted to create this thing where I typed in a formula and it would run it through, it would parse it using KAS.js, and KAS.js has a thing that will, so you parse and that turns it into a data structure, and then the data structure you can turn into tech code, and then the tech code I wanted to turn into HTML using KaTeX and to display it here. You might notice this is not KaTeX. Eventually I had to completely change how I was approaching this problem. But my goal was to create a formula here, and then also to be able to show the parse tree, right? So one of the nice things about the structure that KAS.js gives you when you parse a particular formula, right? It gives you a structure, and that structure is just it's a recursive tree, right? It gives you a sense. You can iterate over the tree, you can draw the tree, and it encapsulates all the information that you need for the formula in this tree-like structure that's ready to be manipulated using either the pieces of the KAS library, or you can create your own syntax tree manipulators. So anyway, this is what one of those trees looks like. So for this formula here, x squared plus 2x plus 1, it says, okay, so the main thing that this is addition. And we're adding three things together. We're adding x squared, and x squared is a power of x to the power of 2, and we're adding 2x, which is a product of 2 and x, and we're adding 1, which is an integer, right? So it has all of these structures within structures within structures, and that encapsulates all of the information about the mathematical formula. So I wanted this, and I wanted this in particular because KAS.js is actually it treats things a little bit interestingly. It treats division as multiplying by x to the power of -1, and it treats subtraction as adding a negative, which has some advantages. It certainly makes things easier to manipulate, but it also changes the formula, right? If I say division, I'm not thinking about multiplying by x to the negative first. So, kind of an interesting thing. You can play around with these formulas and the way that KAS displays them. I think eventually I got rid of most of that stuff from this interactive. This interactive here has, I think, very little KAS and KaTeX. Well, it's got KaTeX, but it has very little KAS remaining in it. But anyway, the other thing that I wanted this interactive to do is to display the formula, but then when you hovered your mouse over pieces of the formula, it would recognize what piece of the formula you were hovering over and highlight the corresponding subtree of this syntax tree. So I thought that would be kind of neat. It should be pretty straightforward as long as I have some way of connecting this particular bit of HTML, right? This particular object on the screen with the part of the formula that rendered it. And then I can just do, hover stuff, and whenever you change what element you're hovering over, it changes what part of the tree gets highlighted, and so on and so forth. So I thought, oh, this is going to be fairly simple, right? Well, not so much. So my idea was I wanted some way to be able to imagine that this is some formula that had gotten output by KaTeX. I needed some way of tagging each of the pieces of HTML, right? Each bit of these formulas, each of the things that I can highlight is, I think it's a span in the HTML file. And so I needed some way of being able to find those spans, being able to find those HTML elements and identify where they came from. And so this was my solution, this function here. So this function, I call it modtech. So what it does is it iterates through one of these data structures, this syntax tree data structure, changing the .tech function. So each structure had a .tech function, and that .tech function tells the structure how to convert itself into tech code, which I could then turn into HTML through KAS.js. So anyway, what this does is it just iterates through. Of course, if it doesn't see a fancy formula, it just says, well, you know, like we're down at the bottom of the tree. This is fine. Don't do anything. On the other hand, if we have some sort of node of the tree, node of the structure that had as subnodes, that was built up out of smaller pieces, what I did was I took the currently existing tech function and renamed it to old tech. And then I created a new .tech function. And this new .tech function would first call this old tech function in order to get the tech code, and then it would put a box around it. So here's, you know, the escaped LaTeX code to put a box around something so that I could identify it later on in the HTML. It turns out that KAS.js actually recently added some support for specifically tagging HTML elements. So if I had gone this route, it would have become easier with that update. But anyway, I wanted to tag this particular HTML element, and the way that I thought I would do that is by putting a box around it, which I could then recognize the HTML that corresponded to an element that had a box around it. And the fun thing is, so not only would that change the tech function for an object, but I would then iterate over the subformulas of that particular data structure and modify the .tech functions for all of those subformulas. And because this is absolutely remarkable that this even worked at all, because each of those, so the way that the .tech function worked was recursive. In order to take a particular structure and turn it into tech code, what it did was it took all of the subformulas and worked out what their tech code was, and then based on how they were combined, were they being added together, were they being multiplied together, is this division, is there square root or something that we have to deal with, however they were being combined together, it would then combine the tech strings together appropriately to produce the HTML for the bigger object. It's remarkable that this worked at all, and this code does in fact work. Let me actually show you it in action. Hold on, I need to actually let's So here, what I've done is I've told KAS to parse this particular string and return to me the data structure that describes this particular string as a mathematical object, right? It returns the syntax tree as a data structure. And then I'm going to so first I'm going to show you what here, let me actually show you this string. So here I'm going to take K.tech. Let me even go one more step and show you what K.tech looks like. So K.tech is the tech code for this particular string. It's actually fairly simple. Maybe we should make let's make this string a little bit more interesting. And then we will do K.tech again. And as we can see, we have some valid LaTeX code that would render itself as this particular formula nicely. So now I'm going to, now we can do so as you can see, we can take this, we can call kotech.render to string on this tech code, and what it will do is it will produce a new string, and this new string is actually a bit of HTML code. It's got some accessibility features, and it will also render as the particular formula that we're trying to render. So for instance, we can now do we can now set this, the inner HTML of this particular element on the web page, to be this particular code. And this particular code, when we render it on the web page, winds up looking like a very nice version of, this looks like proper tech, proper LaTeX rendering. Very nice version of our original formula, which was originally just a string. So one of the things that we can do is we can take our expression, what did I call it? I called it K. So K is the data structure that stores this parse tree in it. And what I can do is I can call this function called modtech. And again, that's going to iterate through all of the substructures of K, and it's going to change their .tech code. And so now this new structure, notice that this new structure now has an old tech function and a new tech function that have been changed from what they should be. And then I'm going to there we go. I'm going to take this K, let's actually just do K.tech. Sorry. And we can see that what this has done is it's changed the function. And it's not only changed the function, it's changed the function recursively, so that all of these pieces of the structure have now gotten boxed, except for one that has to do with how things fell through in this base case here. But essentially, it put pretty much everything into boxes here. Oh, no, actually, the reason why it's doing that is because it's thinking of the fraction 1 over x as x to the minus 1. And so this 1 here, according to KAS, isn't actually real. Oh, that's really neat. Okay. So anyway, what I did was I went and I recursively added these boxed things. And again, boxed is just LaTeX code that's going to put a box around everything. So what we can then do is we can do this again. We can take this tech code and we can render it to string, so we can turn it into HTML code. So here's the new HTML code. It's a little bit fancier than the old HTML code, although honestly it's really hard to tell the difference. Just by looking at it, this HTML code is not meant to be read. It's meant to be rendered. And then we can take this and then we can do document dot. Here we go. We can change. I'm going to change the HTML of this particular element on the page to be this newly rendered string. And there we go. We've managed to put boxes around all of the different subparts of this formula. So this Montech code really does work, and I thought that this really was the way of being able to, we have this formula and I need to grab all of the pieces and to be able to link them to where they came from. And okay, I can do that manually because the nested structure of the boxes matches the nested structure, the substructures or something like that. I wasn't sure how I was going to get this to work, but I thought that this was a good start, and it allows us to see all of the different pieces that make up a formula. There's only one slight problem, which is that I have permanently changed the way the tech renders things. Sort of, kind of. Let me show you one of the things that happened that just made me give up on this whole approach. So here I had, so here I suppose that I wanted to, instead I had this formula here, and I wanted to put, let's see if I can do this manually. So So here I have, I've taken the square root of x plus y and I've rendered it as an expression. And we can actually take a look at what that structure looks like. Instead of thinking, so the way that KaTeX thinks of square roots, it doesn't actually think of them as square roots. It just kind of remembers this was a square root and it stores it as a power. It stores it as raising, in this case, x plus y. It stores it as raising this addition, this x plus y, raised to the power of rational 1, 2, which is how it stores 1/2 as a number. So it thinks of the square root as x to the 1/2 and then remembers that it was a square root so that when you draw it, it looks like a square root. But doing this just makes the math a little bit easier. Let's there we go. So what I've done is I have changed the inner HTML of this particular element so first I took this structure, turned it into tech, and then rendered it to string. So and then plop that into HTML. So k.tech currently looks like this, right? This is how this is how KAS knows to turn K into tech code. Now, let's introduce a new variable. and it's going to be a new square root. So this is a completely different square root, right? Before we were talking about the square root of x plus y, now we're talking about the square root of 2. So of course, j.tech is going to look like this. And one of the things that we could do, if we wanted to, and as part of this, this tree drawing program, what I wanted to do was I wanted to apply ModTech to everything that I wanted to draw. So let's take J and let's apply ModTech to it. And so what that does is it changes j.tech so that now each of the subformulas, I mean there's only the formula itself and then the subformula too, but each of those formulas we're putting a box around it. And now for the fun part. Let's take a look at I should have looked at this before, k.exp. So k.exp is a rational one too. And you might notice this already. We've changed k.exp, even though I didn't touch k at all. I haven't touched k at all. Go back in the video. You will see that I haven't touched k at all. Nonetheless, we have changed changed the tech function and created this old tech function for k.exp. And what this means is that if we wanted to k.exp, so k.exp is just, it's the sub tree, the substructure representing that exponent. So k.exp.tech. I've put boxes around it. So somehow by running this ModTech on a different square root, right? I ran it on J. I didn't run it on K. By running this on a different square root, it has changed k.exp.tech. It has changed how this particular subformula of K gets rendered. And it doesn't actually change how K gets rendered. K gets rendered just fine. But the issue was when I went to draw the tree, this one particular sub part of the formula, the tree, the bit of the tree that corresponded to this particular sub part of the formula, wound up having this extra box in it, and it was really weird and very hard to debug. But anyway, what's going on? Well, the key thing is that somewhere in KAS.js is this particular line of code here. Num.sqrt, so this is some sort of constant that it's remembering is the number or the exponent that corresponds to square roots. And in particular, what it does is it creates a new rational, 1, 2, so just, the rational number 1/2. Here it's adding a hint that this is actually a root, right? So it remembers, oh, x to the power of this. I should write that as the square root. I should not write it as x to the power of 1/2, because there are some cases that you want to write as x to the power of 1/2, and there are some cases that you want to write as x as square root of x, and it uses this hint to distinguish the two, as opposed to somehow rendering them, somehow storing them as completely different structures. And this num.sqrt is used to turn square roots into powers. So if we see a particular square root, it's going to, when it's trying to put together the formula, it's going to return a new power of the argument to the power of num.sqrt. And because it isn't creating a fresh, new rational 1, 2 at that particular part of the code, it's reusing the same rational 1, 2. It's using num.sqrt is actually a pointer to a fixed number 1/2 somewhere in memory. And so what that means is that when we change that 1/2, that magical reference 1/2, when we change any bit of it, in particular when we change its .tech function, what that does is it changes the .tech function for anything else that points to this magical 1/2 function. So in particular, any other square root structure. Anyway, ultimately I wound up doing everything by hand because this is absolute nonsense, and I really wanted to make sure that I was doing everything correctly. KAS uses a different type of one of the fun things about JavaScript is that it has many different, very different types of object-orientedness. You can do object-oriented programming in radically different ways. I didn't like the way that KAS.js was doing it, so I decided to eventually make my own, well, just the bits that were necessary in order to put together this particular parse tree generator that you are welcome to play around with at home, and I will link you to in the comment in the description below. So anyway, that's a fun story of a thing that happened to me. I hope you found this video enlightening, enjoyable, funny. I don't know. It's a weird, hacky thing that happened when I was trying to do things that you aren't supposed to do with KAS.js and KATEK.js.